Dear learners, we will be talking about the transformations of mineral compositions both in terms of generation of new minerals as well as changing of composition in metapelites. The metapelites are basically transformed clastic sedimentary rocks which are commonly known as shales. They represent a large population of rocks which have characteristic mineralogy. Metapelites commonly contain minerals such as garnet, biotite, staurolite, chlorite, muscovite, cordierite, chloritoid, aluminosilicate and quartz, and we require special diagrams for these. J. B. Thomson devised a diagram which are known as AFM diagrams for these. The reason we require these special diagrams for these is because amongst the minerals which I listed, 70% of the minerals contain iron and magnesium, and the changes in metamorphic transformations in these occur by change of proportion of iron and magnesium. So, if we club these two components together as we did in HCF diagram, the way the changes occurred cannot be detected. So, therefore, we require a new diagram for this. That diagram is called as AFM diagram, where as you can understand the F and M represents the iron and magnesium part of the component. In arriving at this diagram, there are some problems. The problem is because when we reduce the component by not considering SiO2 and considering it as a separate pure phase quartz always present, we still are left with at least 4 component, that is Al2O3, FeO, MgO and K2O. The K2O, unlike in basalt, is an important constituent of the pelitic sedimentary rocks which get transformed to metapelites and therefore, cannot be neglected. If we consider all the 4 elements and all the 4 components, then we are presented with a tetrahedron. Let us look at this tetrahedron. This tetrahedron contains here A, that is Al2O3, K which is K2O, F which is FeO and M which is MgO. The minerals which are commonly present in the metapelitic rocks include chlorite, which is an iron magnesium hydrous mineral. So, it plots on the AFM phase, chloritoid which is an iron bearing aluminosilicate which plots on AFM phase, the cordierite which is a magnesium bearing phase and plots again on AFM phase, garnet which also plots on AFM phase. But there are 3 minerals from amongst those listed which do not plot on AFM phase. These are muscovite, biotite and potash feldspar. Biotite, because it contains all the 4 components, that is K2O, FeO, MgO and Al2O3, plots inside the tetrahedron, and it is very difficult to distinguish biotite which is present inside the tetrahedron with, let us say, chlorite which is present outside or on AFM phase. So, the solution of this problem is arrived at by projecting the phases or minerals through a potassium bearing phase. For this we choose muscovite. Now, the formula of muscovite is such that it contains K Al3 Si3 O10 OH whole twice, and the formula of biotite is K Mg2 Fe and Al Si3 O10 OH whole twice. So, the amount of aluminum in biotite is 1/3 that of the muscovite. So, if we project biotite through muscovite, it intersects biotite inside the tetrahedron and comes down and comes below the FM line. For that reason, the AFM diagram is kept open from the lower side, that is AFM line is not joined. Just to illustrate this, I will explain how this is plotted. A in biotite is -1, because the projection is from muscovite. For projecting from muscovite, we need to reduce the Al2O3 by the amount of Al2O3 which is associated in muscovite. Since for each mole of potassium there are 3 moles of Al2O3 which are associated. So, we have to subtract Al2O3 minus 3 K2O for muscovite projection. So, therefore, it becomes Al2O3 minus 3 K2O and the value comes out to be -1, and F is 1 and M is 2 for this particular biotite, and therefore, that biotite will plot here, and in AFM projection it will plot below the line, because the value of A is -1, that is below FM line. So, again to recall, A in AFM diagram is computed by plotting A is equal to Al2O3 minus 3 K2O. When we are projecting it through muscovite, it is considered that muscovite is always present in assemblage. So, it is quartz plus muscovite. However, in some of the metapelitic rocks at very high grade, muscovite is consumed or finished and it transforms into another potassium bearing phase, which is potash feldspar. Now, in potash feldspar, the proportion of alumina which is associated with potassium is equal, that is, for 1 mole of potassium 1 mole of aluminum is associated. So, when it is projected through K feldspar, then the subtraction of aluminum for potassium is 1, Al2O3 minus K2O. However, when it is projected from muscovite, the subtraction of aluminum is 3 times that of the K2O. So, in this way the AKFM tetrahedron can be reduced to AFM phase. Now, this is the AFM phase. Here Al2O3 is at this end, FeO is here, MgO is here. As you can see, the F and M lines are extended below 0 aluminum line, that is below minus aluminum line. So, this AFM projection was devised by J.B. Thomson in 1957. There is 2 ways of plotting the various minerals in this diagram. One of the way is similar to what we learnt in ACF diagram, that is the A pseudo component of any mineral is equal to A by A plus F M, and then we will get a coordinate and we can plot that. Or in other way, one can draw an alumina index lines for projection through muscovite. This alumina index is calculated by this formula, that is Al2O3 minus 3 K2O divided by Al2O3 minus 3 K2O plus FeO plus MgO. And these lines, for example, this is minus 0.5 alumina index line, this is 0 alumina index line, this is 0.5 alumina index line, and this is 1 alumina index line. Now, for any mineral, we calculate the MgO by FeO plus MgO. that in mole percent is plotted on FeMg line and that is connected to Al2O3 line. All along that line, this radiating line, the alumina index, the FeO by MgO ratio is same. For example, for this 0.2 line, the FeO MgO by FeO plus MgO is here 0.2, here 0.2 and here 0.2. Everywhere this value will be similar. So, these are equal FeO MgO ratio lines and these are alumina index line. Their intersection for a particular mineral gives us a plotting position. For example, for a staurolite, this plotting position we have an alumina index of 0.7 and an Fe MgO by FeO plus MgO value of 0.1. So, that will tell us that the position of staurolite is here. For potash feldspar projection, the FM line need not be closed because biotite comes within the triangle. So, that is the difference. Now, for both, if it is projected through muscovite, then we will write here quartz plus muscovite and it will be assumed that quartz plus muscovite are present in the assemblage. If it is projected from potash feldspar, then it will be quartz plus potash feldspar and it will be assumed that quartz and potash feldspar form part of the assemblage. Let us look at some actual example of looking at these minerals and showing these minerals on AFM diagram. Now, in this photomicrograph of a metamorphic rock from Karakoram, the garnet is present here, staurolite is present here and in matrix the foliation is defined by biotite. So, if we find the textural equilibrium between garnet and staurolite here, for example, this is also staurolite. So, we find garnet, staurolite and biotite together, then that will be represented by a triangular space here and this thin section is well represented by such a triangular space and it tells us that quartz and muscovite, because this is an open ended one, tells us that quartz and muscovite are also present in the assemblage. When we look at the triangular areas like this in AFM diagram and also in other compatibility or phase diagrams, the relationship of number of phase equal to number of component is defined. Now, that relationship of number of component and number of phases equivalence is for degree of freedom of 2, that is for a range of pressure and temperature. So, when P is equal to C, the number of components are equal to number of phases is also known as Goldschmidt's mineralogical phase rule. If we look at metapelites, each zone in this way, which is marked by appearance of an index mineral, is representing 2 degree of freedom, because once in an index mineral has appeared at a particular pressure and temperature, it will continue till such time the next index mineral does not appear in a metamorphic sequence, and the next index mineral will appear at another pressure and temperature. So, the area between these two, that is the range of pressure and temperature between these two, will define a range, which means 2 degree of freedom. So, each zone in this way defines 2 degree of freedom and each zone can be represented by one AFM diagram or one AFM type of diagram. Similarly, or by implication, an index mineral will define 1 degree of freedom, because that is defining a specific appearance of a mineral, and that is by normally by change of tie line. And as we saw in ACF diagram, when change of tie line in such a way that crossing of tie line occurs or tie line flip takes place or topology of the diagram changes, then that represents a univariant situation, which means 1 degree of freedom. So, an index mineral defines 1 degree of freedom, a zone defines 2 degree of freedom. Besides this, in many minerals, because minerals are impure phases, they continue to exist, but with change composition. To illustrate, if there is a garnet and biotite at lower pressure and temperature condition and the rock continues to increasingly experience higher pressure and temperature condition, the composition of biotite and garnet may change, but no new mineral may form. When that happens, that is called as continuous reaction, where no modes or no new minerals are forming. That in diagrams like AFM is represented by rotation of tie line, that is, the coexisting tie line gets rotated, for the reason that the iron and magnesium as phase component, this redistribution does not go equally. That is, with increasing temperature, more magnesium goes to biotite and more iron goes to garnet. So, dear learners, we have learned that what are the common minerals of metapelitic rocks which are present in metamorphic metapelitic rocks, and which is the way to depict them, their changes through AFM diagram, and also that two major kinds of changes may occur. One, which are represented by tie line flips, the other continuous changes which are represented by tie line rotation. Thank you, learners.